Welcome to the fifth episode in the OpenCL video series. My name is Dave Gohara, and I'm with macresearch.org, as well as with the Center for Computational Biology at the Washington University School of Medicine in St. Louis. In this episode, we're going to do questions and answers only. It'll be a really quick episode. I've been really busy, so I apologize, and I haven't had much time to devote to putting these together. Some of them can take quite a bit of time to put together. So my apologies in the delay in getting some of the questions answered, as well as for delay in getting the next installment put together. But hopefully over the next couple weeks I'll be able to find some time to put together some more episodes and get those out. As always, if there continue to be questions or or other questions come up or things like that, feel free to send me an email, and I will do my best to answer the question or post the question to the macresearch.org forums. I monitor those as well, obviously, and so if it's something that people are asking a lot of, obviously I'll try and do it as a Q&A. If it's just a one-off or something very specific, I'll usually just try to get back to you via email. But again, things have been really hectic around here, so if there are some delays, I apologize for that. Before we get to the actual questions and answers, I want to just do a quick thank you once again to our hosting provider, Macias. If you are looking for hosting services, managed services, I'd encourage you to check them out. They've been really great with us. And, especially with this sort of uptick in bandwidth and the amount of just general traffic that's been going to the site, it's really gone up in the last couple months. And so they've really been doing a great job for us, and we're really thankful. So thank you very much. And with that, why don't we start with Q&A. So Q&A is really simple. There are just two things. One was there was a couple questions that came in about like GPUs, and I think it was really the questions were really around terminology, I think, and so I'll try to address that and just talk about like GPU layout on the current series of hardware, or at least the hardware we talked about in the last episode. And then also there was a question regarding bank conflicts, and so as you'll recall in the last episode we were talking about memory access, memory layout, shared memory specifically, and how to use it, what constitutes efficient access or not. And so and then this concept of bank conflicts came up, and I towards the end I gave a very specific example about matrix transposes and why you would get bank conflicts, but I didn't really provide an actual detailed portion, like a representation of it. And so I'm going to try to do that here, just sort of reformulate the matrix transpose in terms of why you would get bank conflicts under a very specific set of conditions, and hopefully that will address the question that the person had. And actually there wasn't only one person, there were actually multiple people who had this question, so hopefully this will address it for all of you. If it's something that you just missed or just wasn't clicking or whatnot, hopefully this will make a lot more sense when we're done. So that's what we'll talk about. So starting with terminology like GPU layout and things like that. So what I did was I grabbed this portion. This is from an NVIDIA slide, actually, from I think one of their standard slides. You'll see it quite frequently in their materials and talks that NVIDIA gives. And so, but I think it's actually neat and clean enough that it's easier to make the point with this. And so this whole black area could be considered let's say the GPU. And in the 10 series, the GPU consists of 10 thread processing clusters. So that's this sort of darker gray box. Each one of these gray boxes represents one thread processing cluster. If we drill down a little bit and we look at this sort of lighter gray box, there are 3 of these lighter gray boxes per thread processing cluster. These lighter gray boxes are our streaming multiprocessors. Okay, so that's the next level of hierarchy in terms of the functional organization of the GPU. So the black box is the GPU portion itself. The gray box, the dark gray box, is a thread processing cluster. Going down next is the streaming multiprocessor, and Each thread processing cluster has 3 streaming multiprocessors. So in the 10 series architecture, we have 30 SMs per GPU. Then when we drill down even further, we have these sort of little orange boxes that we refer to, well, actually, depending on who you talk to, they might refer to it as something different. So these are either called cores. More commonly, they're called cores, but they can often be referred to as scalar processors or streaming processors. And this is, I think, where a lot of the confusion comes from, because you hear this term core, and it's really like, what are we talking about? And the use of the word core is completely different than the use of the word core on a CPU. And I'll explain that a little bit more in a second. But each one of these orange boxes represents the next kind of functional or a functional unit on a streaming multiprocessor. Each streaming multiprocessor has 8 SPs, or 8 cores, okay? And because there are 8 per streaming multiprocessor, we have 30 streaming multiprocessors, we have 240 cores. So when NVIDIA says they have 240 cores, what they're referring to are the streaming processors, okay? Now, what is this actual core? What does this core actually do? This core primarily does ALU and FPU. Okay, floating point is the floating point unit and the arithmetic unit. Okay, and this is different than what we would refer to as a core on a CPU. On a CPU, when we're talking about a core, we're talking about ALU, FPU, but we're also talking about vector units, perhaps a memory controller, caches, of course. All of that stuff would be on a core. That is not what they're talking about when they're referring to as a core here. And part of this may be marketing, because 240 cores sounds a lot better than 30, and 30 sounds better than 10. So you can kind of see where this goes. So, but when they're talking about cores, they're talking about these little orange blocks, and this is where your floating point, single precision floating point arithmetic is occurring. Now, there are other units on other portions of hardware on these streaming multiprocessors that are shown here and that also aren't being shown here. One of them is the double precision unit. So in the latest series, there's dedicated hardware for double precision arithmetic. There's 1 double precision unit per SM, which means we have 30 double precision units total. And then each SM also has 2 special function units. And so that means there's 60 special function units per chip, or per GPU. And if you'll recall, the special function units are things that do things like transcendentals, reciprocal square roots, things like that. So transcendentals being sine, cosine, those kinds of operations, but they're obviously being done in hardware. So there's dedicated hardware for those kinds of things. And then, of course, we have local memory, which is our shared memory that's used for sharing information between threads and work items, work groups that are running on each of the cores. So hopefully that kind of clears things up. But the important thing to keep in mind and to note is that the terminology that's used for CPUs is not one-to-one with the terminology that's used for GPUs. And I think that makes it a little bit confusing. And specifically when we're talking about cores, we're not talking about the same type of logical unit on the GPU as we are on the CPU. So remember that a core is we're talking about ALU and FPU on ALUs and FPUs on the streaming multiprocessors. So hopefully that clears that up a little bit more. And again, if there's still more questions, then I will I'll try and explain this a little bit better still. So the next part is bank conflicts and local memory. And so the previous episode was really dense. There was a lot of stuff, but I think the part where people had the most questions were with regards to bank conflicts, and specifically a very specific kind of bank conflict, and why it would constitute, why in the example I presented, that would the way you would read memory or access the memory in the local memory would generate bank conflicts. I stated it when I spoke about it that we would actually get bank conflicts, but I didn't give an example or show in a diagram why that would be. And so I put together a slightly different diagram that will hopefully make it a little bit more clear. But let's just do a quick refresher with regards to local memory. Local memory on current hardware is 16 kilobytes. That local memory is broken up into 16 banks. So each bank is effectively 1 kilobyte. That means each entry in the banks is 32 bits wide, so 4 bytes, which means that per 16 kilobyte block, we have 4,096 entries in total, okay? Now, the important thing to remember about these banks, okay, again, they're 1 kilobyte in length, all right? But the important thing to remember is that successive 32-bit words are assigned to successive banks, okay? If you can understand this concept, and hopefully you will once we're done once we're done with this presentation. If you can understand this, then you'll understand why we're getting bank conflicts and why we'd get bank conflicts under certain circumstances and under other circumstances we wouldn't, okay? And the other important thing to remember here now is that whether we're reading or writing, okay, 2 or more simultaneous accesses to the same bank result in a serialization, okay, of the memory access, and that serialization is what we refer to as a bank conflict, with, of course, the one exception. That is, if all threads in a half warp access the exact same bank, all right, the same entry, that does not result in a bank conflict. And it has to do with what's called, that bank is usually given what's called the broadcast word, and there's special handling for that situation. But all other situations where you might have 2 threads accessing one bank, let's say simultaneously, that will be a result in a bank conflict. If you had 3 or 4 or 5 threads accessing a single bank simultaneously, again, that's a bank conflict, and that's serialization. Only if every thread in a half warp is accessing the same bank simultaneously will you not get a bank conflict. Or, of course, if every thread is accessing them properly and each thread is accessing its own, is accessing an individual bank. For those parts, go back and look at the previous podcast, because there are some diagrams in there that I haven't included here that sort of make that portion very clear, I think. So and hopefully all of that part was clear, but what I really want to address is why we would get bank conflicts in the matrix transpose example as it was presented last time. So we'll do that. So recall in the matrix transpose example, we were talking about, I presented this picture of this field of sunflowers, and basically we're doing a permutation along the diagonal, so from A to C of the values. We're swapping indices, values at the various indices. So going from landscape, in this case, to a more portrait type representation, you see that A and C, the values that would be here and here, would all be the same. In fact, any pixel value along the diagonal here would remain the same, but that the elements say here are swapped. So B and D are now swapped in terms of where they're located, and of course our axes and dimensions have changed. I presented this in terms of a 4-unit half warp last time, and maybe that wasn't the best idea. Maybe I should have done it a little bit differently. But again, as a refresher, basically what we do is if we read in, each thread will read from global memory and write that to shared memory. Okay, these are all coalesced loads, and that also means, because they're coalesced, that we're not having bank conflicts. So we're doing there's a one-to-one correspondence. Every thread is reading from an address, writing it to an address in local memory. There's a one-to-one correspondence. All of those writes are done to aligned locations, etc., and so forth. So that's all one-to-one. Okay, then what would happen is when we want to actually do the transpose part, okay, this thread is going to read from this location. The second thread, or actually really thread 1, so thread 0 is going to read from this location. Thread 1 is going to read from this location now. Thread 2 is going to read from this location, and so on, and we kind of do this. This actually is what would generate this read here. Okay, a read or a write, but in this case a read will generate the bank conflict. And the question is why? You would say, well, they're reading from a different bank, and they're really not. And so I think that this gets sort of obfuscated in the way this diagram is. So the next series of slides will hopefully clear that up. And then, of course, once we've transposed it and the things are actually sort of contained, each thread has the data written to the output, the local memory output array. Then when they write, they all write. It's a coalesced write out to global memory, and so that's all okay. It's really this read portion here in this example where we're going to get the bank conflicts. And so why is that? So what I've done is I've taken the equivalent of one warp. I've created one warp. Remember, a warp is 32 threads. Okay, but on current hardware we really deal with half warps. Okay, so we're talking about 16 threads per half warp. All right, 16 threads, 16 banks. All right, each thread effectively wants to, in an ideal situation, read from a single bank and write to a single bank. Okay, now why would this matrix transpose, if we were to do this, cause a bank conflict? And so what I've done is I've labeled the banks on top of the actual data. Okay, so if this is our data, let's say we have an array of 32 elements or whatever, and it's going from 0 to 31. Okay, each element is 4 bytes wide. Okay, so single precision float or an integer, a 32-bit integer, or something like that. One warp would take us from 0 to 31. One half warp is going to take us from 0 to 15. The second portion of the half warp is going to take us from 16 to 31. But 0 to 15 is going to be assigned to banks 0 through 15. When we read for this data of the half warp, okay, 16 to 31, this will also be assigned to banks 0 through 15. Remember, we only have 16 banks, okay? And each bank, each element is going to be assigned to a successive bank. Each element is going to be assigned, ideally, to the bank whose offset is effectively modulo its corresponding offset in the array. Okay, ideally, all right. And when you're on, if it's aligned, which is what you really want it to be, that means that element 0 is going to correspond to bank 0, 1 is going to correspond to 1, etc. and so forth. Element 16 modulo 16 is 0. 17 modulo 16 is 1, etc. and so forth. So this is how they get assigned to each bank. All right. Now, why do we get a bank conflict? All right. So we've written all this stuff into memory. Okay. So element 0 is being serviced by bank 0. Element 16 is being serviced by bank 0. Okay, that portion is okay. But when we want to read it, okay, we're now dealing with our half warp. Okay, so only focus on the first 16 elements here, the half warp. When we want to do our matrix transpose, okay, if it's 16 elements wide, let's say, this thread 0 is going to read from here, which this element is in bank 0. That's fine. That's not a problem. Thread number 1, okay, which is the one that has element number 1, okay, is going to want to read the 16th element. I'm sorry, well, I guess the 17th element, really, but it'll want to read number 16 here, okay? The number 16 has been assigned to bank 0, okay, because of the way this memory and the way this data has been loaded into the local memory. All right. So what that means is we now have, and when they do this, because half warps all do, because remember, every thread in a half warp moves in lockstep, which means that this thread is going to read this at the exact same time this thread is going to read this. That means that we now have two threads running at the exact same time that are both trying to read separate pieces of data, but where those pieces of data have both been assigned to the exact same bank, the same bank ID, 0. Okay, this is not allowed. Okay, and because it's not allowed, what we end up with is a bank conflict or a serialization. Thread 0 is going to have to read it first, then thread 1 is going to have to read it second, and every time we do this, we end up with some kind of stall. And so this is what's causing the bank conflict. So how do we get around this? Now, I said it the last time, but I didn't really show it. And so the way people get around this is by padding their local data array, and you only have to really pad it by one value. So how does that work? So now when we load data from global memory, which isn't shown here, into shared memory, we load elements 0 through 15, data elements 0 through 15 into banks 0 through 15. Okay, but then we pad the local array by one element. Okay, and we don't use that value. We don't care about that memory location. We never use it. We just assume that our shared memory size effectively is equal to for containing a half warp worth of information is no longer 16, but now it's 17. Okay, and what that means is that when we deal with the next piece of data, okay, it's going to be placed into local memory at an offset. Okay, we're reading from global memory coalesced and aligned, but we're writing to the local memory unaligned. There's no penalty for that. Okay, so basically what we do is we offset everything and we put in this sort of dummy memory, and we just leave it. It's nothing. There's nothing there. It's just whatever, it's just blank. Okay, and then similarly at the end of this one there would be another blank entry, and it would just kind of go down the line. And so what does this get us? That means that when we want to read, okay, element 0 is going to be serviced by bank 0. Element 16 is going to be serviced by bank 1. So when we do the reads for the transpose, right, thread 0 is going to want to read this element. Thread 1 wants to read this value, but it's going to be reading it from bank 1. Okay? So now we've avoided the conflict. We don't have these two threads simultaneously accessing this element. Okay? And then if we were to go down, remember this one here is going to be, so if we talk about thread number 2, okay, thread ID 2, it's going to be reading, there's going to be a blank value plus another one, which means it's going to be offset by yet another value. And so each one of these will be reading successive elements, and they won't all be serializing on the exact same bank. Okay? So hopefully that clears that up a little bit. Let me just go through this one more time, just so that it's completely, or so that it's more clear. Thread 0 is going to be accessing element 0. Element 0 is serviced by bank 0. Thread 1 is going to be accessing element 16. Okay, element 16, because of this padding, is now shifted by 1. So number 16 is really being serviced by bank 1. Okay, if we go down the line, thread number 2 wants to read element number, it's actually not going to be 16, it's going to be value number 32, which will be ultimately serviced by bank 2, and so forth down the line. So each one of these is offset by 1, and that's what gets us all the performance. If we were to go back here actually to this one, and we were to continue with the same sort of model like I just did, remember that this is going to read this element, which is serviced by bank 0. This one is going to read element 16, which is serviced by bank 0. This one is going to read element 32, which will be serviced by the next bank 0. Okay, this is a 16-way. This is a 16-way read on the same bank, but it's a 16-way read on the same bank for different data. Okay. If they were all reading the same data, if this thread was trying to read this 0 value which is serviced by bank 0. This one was trying to read this 0 value serviced by bank 0. This one was trying to read this value, etc., all the way down the line for the half warp, then that would not result in a bank conflict. Again, that's a broadcast and that's allowed. In this case, this is different because they're reading different elements that are all being serviced by the same bank, and that has to be serialized. Okay, so when we go down here, by adding in this padding to the successive groups, we've now shifted everything by 1 for each thread, and we've avoided the bank conflicts. So hopefully that makes things a lot more clear. If not, then I will still try and find a way to redo this, but think about it a little bit more. The key thing here to remember is that we're reading different elements that are being serviced by the same banks in the case of the bank and that's what's causing the bank conflicts. And so we need to shift the things a little bit so that we're reading different elements that are being serviced by different banks. This is how we force them to be different banks. If again, we were just doing a one-to-one read, that is, this guy was reading this guy, this guy was reading this guy, this guy was reading this guy, there would be no bank conflicts. Each one is accessing a successive element, which means they're accessing a successive bank. There's no problems there. Okay. The problem really comes up in this specific example for the matrix transpose because we're accessing at an offset equal to the bank size, which is also equal to our half warp size. So hopefully that makes a lot more sense. And there will be cases where you're going to find that you may need to pad or you may not need to pad. If you can access data sequentially, that is, you can always access thread 0 is always serviced by bank 0, thread 1 is always serviced by bank 1, it's down the line of a half warp, then you're never going to have to deal with these kinds of issues. This is a very special case because we have to then do large strides. We have to do strides of 16 into these various locations, and these strides are modulo the actual bank size, and so this is what's causing the problem. Okay, so hopefully that makes more sense. If not, let me know and we'll go over it again, or I'll find another way to sort of present this or give an even sort of more in-depth example. And so obviously with that, I'd like to just point out a couple things real quick. All of this information obviously is available at macresearch.org/OpenCL. All of the video podcasts are up there. There's some other great stuff on the website. I'd encourage you to check it out. Cocoa for Scientists by Drew McCormack. He's got a great series that he's been putting together on how to use if you're on the Mac and you want to learn how to write Cocoa applications, great programming series. He recently also did cover some things with GCD, Grand Central Dispatch, how to use it, how to begin using it, blocks, things like that. So I would encourage you to check out those posts. Also, if you're thinking of buying Snow Leopard, buying some various other things, we do have an Amazon store. Anything you purchase through there, we get a little bit back on, and the prices are the same as if you buy it through the straight Amazon store, through our affiliate store. There's no difference. So you'd be helping us out quite a bit. So if you can do that, that would be great. And then also I want to point out that NVIDIA also has some online seminar series. They do these things live as webinars, I guess is what they're calling them, but they also, after they're done, they post the videos, and I think they may post slides, but definitely the videos. You can also see the videos, and so they have a lot of great stuff up there. Also just general, like using CUDA, GPU programming in general, OpenCL, things like that. So I would encourage you to check that out. The URL is up here as well, so check that out. And we'll see you next time. Hopefully next time we'll talk about, we'll actually do a real-world example. I promise. I've been saying this forever, but next time I'm hoping we're going to do a real-world example that will bring everything together, where we'll be looking at kernels. We'll be looking at a kernel, how to optimize the kernel, how to take advantage of local and shared memory, padding, things like that. And hopefully then all of this will gel completely, and you'll have something that you can actually work with and play with to really start hopefully understanding this if you're still having some problems. So if you're still having problems understanding this. So with that, I'd like to end this, and I will see you